Hello, my name is Jonathan Hernandez. I am a senior in industrial engineering, and I am presenting for our advanced sensing and machine learning for wire arc additive manufacturing, improved quality, and energy efficiency projects. So to begin, I'm going to give a brief overview of what wire arc additive manufacturing, or WAAM, is, and sort of tour our setup that we have. So wire arc additive manufacturing is a manufacturing technique very much along the principles of 3D printing, where we are depositing metal through welding process onto a sheet in order to create complex three-dimensional shapes, and do so in a layering process very similar to a standard PLA plastic 3D printer. So the question is, what are we doing with this process? What are we exploring? What's new? So a common issue with the WAAM process, and a very important point of interest, is defects. So because it is a welding process, you are liable to issues with current, porosity, cracks, uneven heating during the welding process. And you can see on the plate that we have here that we have some very porous welds, in addition to some very smooth and well-done welds, and we'll talk about that in a later section. So we have our testing area, our steel plate where we create welds. We have our CMT welder. So CMT stands for cold metal transfer. It is a process of heating metal deposition similar to that of MIG. So we have carbon steel wire feeding through a tube with an electrical current running through it, and it is shielded by argon gas to ensure the safety of the operators around. There you'll see welding curtains, and we normally wear welding helmets in the vicinity. So we have the robot arm, which is controlled by a standard controller. This allows us to move the robot arm separately. For safety reasons, I will not be demonstrating it for now. But we're able to move the robot arm across 3D space and create these like lines of welds or other complex shapes. And then on the other side of that, now that we have welds and specific hardware, we need to actually see what we're doing. So that's where this comes in. This is our micro epsilon thermal IR camera, and this is what we use to capture our data for our welds and the data that we are feeding into the ML, which we will talk about later. So this IR camera will observe the welding process, and it'll in infrared, and it'll record temperature data, and each pixel of the image is a temperature. So these it records, it sees sort of a thermal image, classic thermal camera look, and this data gets fed, it's saved into a CSV file as a frame. So every in the same way a camera has individual frames, we capture individual frames of the welding process, but those frames aren't just color pixels, they're more so temperature pixels. And we save that individual frame as a CSV for data processing later. So some of the things that we had to work with, some of the challenges we had to overcome with our project is we had to design some hardware to ensure that the system could actually work. There's a lot more to the system than just the CMT. You have the wire feeding mechanism, and we had to design a custom holder for the entire wire feeding system so that we could get our steel wire through the nozzle and make sure all the hoses were clear out of the way and out of the power supply. Another issue is I have another plate right here. So this is actually aluminum. So when we originally started, we were testing with aluminum, and you can see we had some rough welds at the start, very bubbly, but also some very smooth welds with multiple layers. But what we ended up finding was that the emissivity of the weld itself was too high. So this camera in particular was not able to capture a clear image of the melt pool, as opposed to carbon steel, where it was able to effectively capture the melt pool itself and be able to see. So on this plate we have several lines that we've done, and each of these lines were recorded. We have frames saved, and then we take that data, save it, And you'll see on the poster there's a couple of example frames where we have a very smooth weld where you have the heating, the warm metal that has has been deposited, and then you have the melt pool itself where the arc currently is. Whereas in an abnormal weld, you would see a lot of spattering, some uneven heating, and that results in these porous welds that you see where gases are trying to escape out of the molten metal, and they leave behind these large pockets. And also you see large depositions at the initial stages where the arc has just struck and it suddenly deposits a large amount of material instead of moving steadily. So as we move forward, the optimal parameters, so we're running 90 amps through the system in order to deposit our carbon steel. We're feeding the wire rate at a rate of 235 inches per minute, so that's how fast the wire is moving through the system and being deposited. And lastly, the movement speed of the robot itself in the sort of XY plane. It is moving, we found it best to move at 6 to 7 millimeters per second. However, whenever we wanted to create abnormal samples to compare for our machine learning algorithm, we would intentionally run the system at a 5 millimeters per second, which would create these larger pockets where the material wasn't depositing appropriately, whereas in 6 to 7, it was moving faster, and in conjunction with the feed rate, the IPM, we get these very nice and smooth depositions. And we can use the aluminum as an example because materially it is different. However, we ended up with similar results for both materials. However, for the purposes of this experiment, all the data that is collected through the IR camera is specifically related to carbon steel.
Hi, I'm Amogh Modgekar Desai, and I'll be going over the machine learning aspect of our model of our project. Jonathan just went over the industrial engineering aspect of our project. He spoke about the summary, the background, and the system setup with regards to industrial engineering. Now, I'll talk about the machine learning. So this is the model that we use for our convolutional neural network. The convolutional neural network takes in images and it classifies them as either abnormal or normal welds. The images aren't actually images, they are arrays in which each pixel represents a temperature value. So to help humans see it, we have visualized these images by creating a thermal heat distribution. And here we have a scale that shows that the bright parts are the hottest parts and the blue or black parts are the coldest parts. So now I'll talk about the actual convolutional neural network. I'll start by talking about the input layer. The input layer takes in data from a CSV file, and each image in the CSV file has the dimensions 128 by 128 by 1. As you can see here, this is an image of a normal weld, this is an image of an abnormal weld. To the human eye, you can see a few differences in the two. The normal weld is more of a straight line, whereas the abnormal weld seems to have a bulge, and the normal weld has less spattering compared to the abnormal weld. So that's just the differences to humans, but the CNN is able to identify many more differences. So once it loads up the image, it passes it over to the first convolutional block. The first convolutional block extracts basic features. So the model is looking at the raw image and detecting fine-grained patterns. You can think of it as zooming in on small details like temperature gradients, minor spattering, and subtle differences in heat. Normal welds show small gradients and minimal splatter. As you can see here, the gradient is quite small and the splatter isn't much. Whereas abnormal welds have a very large gradient with a lot of spattering. These features are then captured by the convolutional block. Once this convolutional block is done, it passes it on to the next convolutional block. And at this stage, the model starts focusing on specific regions of the image. It's not looking at every detail anymore. Rather, it's looking at parts of the weld. For example, it might try to analyze where spattering is most intense or where the edges of the weld are clean or blurry. Again, these features differ between the normal and abnormal weld. This layer helps the model understand these differences. So this model, as you can see here, the edges are easily visible. You can see that there's a clear edge there. But around here, you can't draw a perfect line around it. Here you can. So here the edges are easily visible. Here the edges are difficult to distinguish. Again, the spattering is barely visible in the normal weld, and the spattering is clearly visible in the abnormal weld. Once the second convolutional block is done, it passes the image onto the third convolutional block. By the time we reach the third convolutional block, the model is focusing on the overall structure of the weld, the big picture. It's not concerned with small details anymore, but rather the general shape and distribution of the heat. This layer might, for instance, detect whether the hotspot is concentrated and sharp, as you can see here, it almost looks like a square, or diffused and large, as you can see here. It looks more like a circle because it doesn't have any sharp edges. So once all three convolutional blocks are complete, the data is passed on to the fully connected layer, which is the main decision-making layer. Using all the features that were analyzed in the three convolutional blocks, the fully connected layer decides whether the weld is abnormal or normal. And you might be wondering, what is a convolutional block? I keep talking about convolutional blocks. So if you see here, each convolutional block has 5 different layers. The first layer is a 2D convolution. The second layer is batch normalization. This is used to stabilize, speed up training. And a 2D convolution is used to apply filters to extract features. Max pooling reduces the size of the image and focuses on dominant features. Dropout is used to prevent overfitting, and ReLU activation adds non-linearity to the network and helps the network learn complex patterns. In order to make the images usable with the CNN, we had to employ data augmentation. So we use data augmentation to expand the training set. For every original image, we generated 10 slightly altered versions. These slightly altered versions were generated by applying a random rotation, a random shift, a random shear, a random zoom, and or a random flip. This added variance to our data set, which was quite small, and increased our data set from 354 images to 3,540 images, making the model better at generalizing across different weld types and different orientations. In terms of the architecture, as we discussed in the previous section, there were 3 convolutional blocks. Each block contained 5 layers, and then there was a classification block that contained an additional 5 layers. So in total, there were 22 layers in the CNN. Now let's talk about the results of our model, and we'll also talk about how the model was optimized in this section. So we use a sequential iterative approach to tune our hyperparameters. This approach is shown in table 1 up here. I'll be going through this table over the next few minutes. So first, we optimized our dropout rates. We did this by testing different combinations across the 3 convolutional blocks. The best performing setup that we found is here. We found that the dropout rate set to 0.2 for convolutional block 1, 0.1 for convolutional block 2, and 0.2 for convolutional block 3 was the best option, as it achieved an accuracy of 82.6 with 6.5 minutes of training time. Once we found that those were the best dropouts for each of the 3 convolutional blocks, we fixed those and then we proceeded to the next step where we optimized the kernel size. The best option that we found was here. We set the kernel size of convolutional block 1 to 3 by 3, the kernel size for convolutional block 2 to 5 by 5, and then the kernel size for convolutional block 3 to 5 by 5 as well. This achieved an accuracy of 8.42% in 10.7 minutes. The max, once we found the optimal dropout and kernel size, we proceeded to the max pooling size. When we did the max pooling size, of course, we fixed the dropout and kernel sizes that we found, and we then found the max pooling size. So we found the best options to be a 3 by 3 pool size for convolutional block 1, a 3 by 3 pool size for convolutional block 2, and a 2 by 2 pool size for convolutional block 3. This gave us our final accuracy with all our optimized hyperparameters of 89.3%, and the training time was 4.3 minutes. Once we finished that, we just had to figure out which model hyperparameters we were using. We decided to go with the ADAM optimizer with a learning rate of 0.01, and we used the binary cross entropy loss function. We ran the model over 20 epochs. When we evaluated the model, we looked at its confusion matrix, which is shown here in table 2. Out of the 341 normal samples, 318 were classified correctly, while 23 were missed. These misses are known as false negatives. And out of the 192 normal samples, 158 were classified correctly and 34 were missed. In this case, the misses are called false positives. This imbalance between the false positive and false negatives is likely due to our original class distribution before the data augmentation. The data set that we originally created had only 80 normal frames and 274 abnormal frames. This meant that the number of images weren't equal. Because of this, the model had fewer normal examples to learn from. So it probably had a difficulty recognizing them, and this led to a higher number of false positives compared to the false negatives. Now Jonathan will be going over the conclusion.
Alright, thank you Amogh for that amazing explanation covering the CNN model and sort of making that connection from hardware to software. So in conclusion, we found this is a very preliminary study, so this is the first step in a larger series of projects to better optimize the system. So we found with obviously an 89.3% accuracy. We can always work to improve that accuracy, but that is a very good start for our project. And something we'd be looking towards doing in the future is integrating that CNN model or that defect detection system into the robot controller directly, allowing the robot to sort of in real time see what is happening on the table and be able to say see a defect and detect it. And once it's able to really see, have that smart vision to see what's happening in real time, then we can start exploring concepts of corrective measures. So we can relay all the information that the model is collecting, everything that the model is collecting, and sort of connect the dots, make sure that the robot can detect a weld and then do something about it in the moment, and it can learn from its mistakes, really understand what went wrong, what process parameters were in place, and possibly in the future avoid those same process parameters or avoid those same mistakes in the future. And with that, we'll go ahead and close with a sample video of the weld process in action. So thank you so much.
Start.